I've had a few people now very specifically ask me for a tutorial on genetic algorithms, with the logic being that if I know a lot about swarm algorithms, inherently I probably know a lot about genetic algorithms, which would be correct. And the bottom line is that both genetic and swarm algorithms fall under a class of algorithms called evolutionary algorithms, which were all invented in around the 1990s and in the 1990s. And then with these particular algorithms, they're based off of biology, but based off of a different biology than the typical AI that most people think of, right? So when we think of like neural networks, perceptrons, etc., those are based off of the brain. Same thing with like what I've gone into with like Hebbian learning, things like that. They're all based off of the equivalent of the human brain. Whereas with genetic algorithms, they're based more off of biological behavior. So evolutionary behaviors or behaviors of certain organisms. When you talk about swarm algorithms, you're talking about generally behaviors of like ants and bees and swarm type of insects. Whereas with genetic algorithms, that focuses on the biology of the mutation and between organisms, like how like parents pass off their offspring, and that's the general concept of how genetic algorithms work overall, right? So genetic algorithms, they're a search and optimization technique. And what they do is they search a imaginary space, like an imaginary box, right? And then you create agents uh, within the imaginary box, and then let's say you put a problem and a solution within the box, and then so what will happen is that you mutate the parents and the relationships that you have, agents that will go through, and then they'll start off with certain characteristics and certain traits that you define and you map out, and then they will evolve based, like off of like probability. And then, based off of how exactly you set the mutation and the evolution within that, the traits will get passed on to offspring. So, let's say that you have agent one, and like agent generation one, and then you have a father and a mother, and then they pass off like 50% of their genes each randomly to the child, right? Which would be like extremely typical. And then that would be your mutations. And then so each generation would just be randomly mutating based off of the parent genes, right? And then you can set for there, like, and from there, like different types of like ways to uh, better that. Like tournament search is a big one, right? Which says that like, so we have a box, we put all of the agents in a box, and then we put the solution in the box, and we don't know what the solution is, but we can know whether or not we're moving closer or further to the solution, further from the solution. So if we move closer to the solution, pass those genes on. If the parent moves further from the solution, like kill that parent basically, and don't pass their genes. And then so that's kind of how you would do tournament search, right? And you can do and adjust all of these things in any way that you like. Essentially, the overall concept is here, where these like you need this framework within it, but then how exactly you implement the framework is completely up to you. So you have initialization, evaluation, selection, crossover, mutation, and replacement. So it's evolution in action, right? It's parents, they evolve and they select, and then they, based off of that, you get an output, and then they mutate and then pass on their genes, and then you have a new generation that takes over. And then so, very straightforward. I break it down to you exactly how this works within the code as well. So you're just initializing a population, then you're creating your fitness function, then you have your selection, your crossover, your mutation, and your evolution loop. All of this is all mathematics. Okay? So it's all mathematics, and it's all based off of biological principles and biological theories. And then so if you know both of these things, then that's a very good starting place for you overall. The common, like kind of the common challenges with these algorithms is like a premature convergence, and I can't point to that enough, right? They'll settle on a solution extremely quickly, and then even if the solution isn't optimal, like they'll settle on like 80% accuracy, and then if they settle on 80% accuracy, like they're not going to go higher than that without forcefulness. And then like the bottom line and kind of what I want to paint within this as well as like a general tip, if there's a biggest tip that I can give you with working with genetic algorithms overall is to consider hybrid approaches, right? So what I talked about with like premature convergence is with typical genetic algorithms and with typical use cases. But I'll show you within this that these algorithms work best if you don't think of them in the typical sense, right? They're based off of biology and evolution and all of that, but that doesn't mean that we're bound by those same principles. So first, let me show you essentially like the code. Like this is a full version of a basic genetic algorithm solving. In this instance, it's solving for this mathematical equation, right? So I have this target function here, and it's like it's a beast of an equation. It's f times x equals x to the second power, where x is in within an array, and then as well as like array and order of operations problem. Like there's a lot going on within this particular function, right? And we want it to solve for x, and so I run it. And it runs in like 3 seconds, and it solves for x, and it finds that x in this instance equals 1023, right? And then you can see this is, so you have the best fitness and then the average fitness, and then what you'll see, like again, like this is premature convergence, right? But it just happens that it's converging at like 90% already, but it's converging around 90%, right? And then so your average isn't going to go like higher or much lower than that because it's going to be within this narrow band. Even though it's like hitting the best fitness function and it knows what the best answer is, like immediately it's still settling within that premature convergence area, right? And then just that's classic with classical algorithms, genetic algorithms. This is very expected. Not a lot of variance. It's just going to be, it's settling on this answer, right? And it settles on it. You can see every generation except for literally the first generation, and then after the second generation, it's like, here's my answer, and I'm stuck on this answer, right? And if this answer were wrong, I would be stuck on this answer. and then so there you go, right? But so take this a step further. Like again, think of this like in as far away terms from actual biology as you can think of. And then so here's an instance where I'm taking and we're going to utilize genetic algorithms to evolve a chocolate chip cookie recipe, and then just flat out with genetic algorithms, right? And so within this, I put in a bunch of variables within this. So how much flour, the grams of flour between 200 and 350 grams, how much sugar between 50 and 150, brown sugar, butter, eggs, baking soda, salt, vanilla, chocolate chips, bake time, and bake temperature, right? And I give it a range for all of these things. And I'm saying like, here's all of the ranges, and then here's all of the different ingredients. What I want the algorithm to do is to find the ideal recipe, right? What is the ideal recipe and the ideal weight within this? And then so I give it all of what it needs in order to calculate that. And then we run the experiment, and then it evolves, right? And then so our recipe that it recommends in the end is to use exactly 277.09 grams of flour, 87.89 grams of sugar, 109.49 grams of brown sugar, 154.13 grams of butter, 2 eggs, etc., right? And then we want to bake it for exactly 12 minutes and exactly 182.8 grams of chocolate chips and at a baking temperature of 134.75 degrees Celsius. This will give us the absolute purest, best tasting chocolate chip cookie that could ever be in existence, according to AI. And I don't know, like I would be very interested if this recipe turns out to be very good. That would be awesome, cool, right? But there you go. It's literally just using the concepts in this instance of a biological evolution, right? And so all of these things, framing them overall, like so from like the 1950s until the 1990s was like a very like prominent period within like philosophy and psychology, especially around these things, right? Like especially with research around like how does the human brain work, how does nature work, nature versus nurture, etc. This is where all of these debates are happening, right? And then so that's where all of this comes from. And then like, I mean, flat out, like even OpenAI as a company admits that like their research and everything they're doing is based in stuff like this from the 1990s, right? Like, I mean, like flat out, like there's like very few new inventions within AI overall, right? People get so hyped about these things, like especially like diffusion, things like that. There's 30, 40, 50-year-old research papers that you can find out all you want to know about diffusion. Literally just go through and you'll find whatever. Like I guarantee you're not going to discover something new within diffusion. It will be in that stack of research papers that you're ignoring on the subject overall, right? And so just highlighting and pointing these things out, like why was, I guess the last question within that then that people would ask is like, so if these are so cool now, like, and it's 1990s technology, like why wasn't it good in the 1990s, right? And very simplistically, overall, like these like evolutionary algorithms as a whole take significant advantage of multi-core computing. And then within that, like, so multi-core computing now as a concept is about 20 years old overall, right? But I happen to work for like Intel and these companies during this time when all of this started to come about. And very specifically, I would train people on these things, right? So I kind of have that experience within that. And then so during that time and within it, it was in the early 2000s. It was always I would always teach, and it was always taught that we are ways off with regards towards multi-core processing, right? At that time, it was the hardware was just starting to catch up, but the software hadn't caught up. So when you're talking about multi-core processing, it's both a hardware function and a software function. The reason why NVIDIA is blowing up so much as a company is because NVIDIA like has for the last 20 years now everything around this particular problem, this multi-core problem, and being able to optimize computing in a multi-core fashion is what NVIDIA has based themselves off of. And then essentially what that breaks down to is if we take like a computer and we realize it as like a block, right? So we can recognize we have like a block of computer, or we can split that block into 10 smaller blocks or 1,000 smaller blocks. The smaller blocks that we have, stacking them together, we can run like parallel process. We can run multiple things at once, right? As opposed to just the one big block of compute. And then so that's the advantage, and the difference there is that same amount of power, that same amount of compute, that same block, but if we just break it apart like 1,000 times, it's actually far more efficient overall. And we can, if we're doing multiple tests at the same time, we want like multiple results all at once, we can do that like over 1,000 tests in the same time as like one test for the big block, right? And if we don't need the big block of compute, it works out. And then that's where these types of algorithms come in. It's like, let's give it the core logic that it needs and core instructions so that it doesn't rely on massive amounts of compute, and we'll just give each little agent a little bit of compute, and it all comes together. And then there you go. And then that's basically genetic algorithms in this instance in a nutshell. And then so again, big difference between like genetic algorithms in this instance and swarm algorithms would be that like, so genetic algorithms are very specifically based off of that biological process of passing on your offspring to the parents and that mutation of the parents, whereas with like swarm algorithms, they're generally based off of particle swarm optimization, so optimizing based off of like pheromone type of principles, and everything that is like associated with all of that. And then so they are very similar in the evolutionary process, but then very different, right? So the genetic process is very different than the swarm process. And then so hopefully that gives you understanding overall and a gentle introduction to genetic algorithms. If you like this type of content, please like and subscribe. Thank you very much.